Our topic for today is section 10.5 areas in polar coordinates. But before we start the section, we would like to do something that's a little overdue, and that is how do we use graphing calculators for topics in chapter 10. So we'll first look at the ways to use graphing calculator to do topics from sections 10.2 and 10.3 parametric equations, and then we'll address polar coordinates as well and continue with our topic for today. So I will revisit one of the problems that we discussed in section 10.3, and that problem you can find in the notes. And generally we were discussing the equation of the tangent lines of the point where the curve crosses itself. That would be example number 24 in section 10.3. So we want to use calculators to illustrate all this. So here's what we do. We turn on calculator as usually, and then the main thing here is to adjust the mode. So here is the mode. So we adjust the mode, and then on line number 4, we choose here. Normally, line number 4 in whole pre-calculus and calculus course was here on the function. Now we go to the second spot, which is parametric. So when we do that, and exit that, and when we do y equals, then what happens, we have two lines to enter both x and y, and when you press x, where the variable normally is, it will type t. So for that problem, we would get t cubed minus 6t, and then we would get t squared. And we got two tangent lines at that point, I don't know if you remember. Then we want to graph this. So let me try graph, and then we will see if we like it. So here it is. Here is the graph, and shows you all that what we discussed there. We drew it by hand in that section, but here's how calculator nicely and quickly does that. And also you see the dynamics, how it goes when the time elapses. By the way, we can adjust the window the same as we normally do. We like time. Time was between -5 and 5. Normally they put 0 to 2 pi because they are used to do circular objects. So I have to adjust this to -5. Here is for the resolution. Maybe I don't need -x. So maybe here I would go just from 0 because I saw that it's all positive. So now when you graph it, you get a much cleaner picture. Look how much nicer it is. And then we asked for two tangent lines. One that's when we come at -t, and one when we leave at +t. So here is what you can do. Here there's a yellow command, the draw, about program. So you go second draw, and you choose what you want. We'll go tangent line. And then they ask us what is the time. If you remember when we calculated, negative time was -√6. I plug in -√6. I press enter, and here's that tangent line that we calculated last time. And then the same thing, I'll say again, second draw, tangent line, and now I'll say what? My time is √6. Here it is. Now we see both tangent lines. All right. So that's one of the illustrations how you can use parametric sub-menu of the graphing menu. And then let's go and see how to use this for polar coordinates. Let me pull out our section for today. And that section, as we said, is area and arc length of the in the polar coordinate. So you will see in the moment, we will analyze the petal. And the petal has equation, let me write it on the board, r equals 6 sine 2 theta. So r equals 6 sine 2 theta. And then I like to draw this, so what do we do here? Now we change our mode, so we say mode, now we want to draw in polars. Here it is, polars. We get out out of there, and then is our window okay? It might be, might not be. Let's try it, and then we'll adjust. So we will go y equals, and then we will enter r equals 6 sine 2 theta. So whenever you do something here, making sure that your angle is in radians, that was fine. So r equals 6 sine 2, and then when I press button for variables, now it types theta. I just graph it. So here it is. And then not bad, because I will really need to find the area of one petal. Looks like it did the whole petal, but maybe to see everything, maybe I should adjust my window. So what would be the window? Probably you see easily that period here is just pi, because if we go from 0 to pi, then the values repeat. But I will draw all the way from 0 to 2 pi, so that's good. They automatically adjusted that, that's good. Theta steps does the resolution. X minimum was okay. Probably what I didn't like is maybe this Y minimum. I want to go maybe -10 to see the whole thing. So here is the graph. Does one petal, does the other, third, fourth. Look how nicely and continuously it goes. So here is the whole petal. Why is this central part missing? That's because of the resolution. So if you want really to see that part better, then we go theta step to be maybe 0.02, so that this will go a little slower because it will go with more details. So here it is. It will come somewhat slower. And then again, if you are still unhappy to see what's happening at 0, then what you can do is definitely zoom in here or adjust your window, and that will tell you. So this curve really intersects itself more than once. So you will see in the problem, they will ask us to find the area of one of these petals. So not just this one. So I say, all right, that petal actually happens until r reaches 0 again, and that's at pi over 2, because 2 theta is then pi. So I'll just restrict myself in the window. I'll say, no, just give me 0 to what, pi over 2. Get only one petal, then theta step is okay. I don't need negative x's. I don't need negative y's. Maybe I don't need x to go that far. 6, no, that's scaling, sorry. X scaling is 1, doesn't matter. And then x maximum, maybe I'm 6. The method something, let me see, y maximum. I also want 6, so I'll graph this. And here is that one petal, as I said, it comes back to 0, but it just doesn't show it all the way. So that's how you use this how to use calculator to draw polar curves. And at this point, I'll just turn off the calculator. If you have some questions about calculator, please let me know, and then we'll continue with our standard material. So, here is the title, area and arc length. Actually, I didn't put a complete title. I better do. So, area and arc length. Arc length in polar coordinates. Generally, what we do here deals with basically 2 formulas. So the first formula deals with the area. So what do? If we have something that we call polar sector. So the same way as before we had vertical region or horizontal region to calculate areas and volume sometimes. Here we have polar region. So polar region has one ray coming from the origin in the beginning, one ray at the end, and then there is some curve limiting that. So it's like curve-sided triangle, and the equation of that curve is r equals r theta. And then what? So we want the area, so this is the starting angle, theta equals some alpha, theta equals beta, and we want to learn how to calculate this area. So formula says that that area equals 1/2 integral from alpha to beta r theta squared dt. And that's what we need to remember to do a problem for practical purposes. Very often in this course, I kind of advertise some material saying this is very important for this is very important for that. This formula is not really important, particularly if your next course is Calculus 3. In Calculus 3, we'll learn a much better formula using double integrals that's just much more natural, and then this expression comes very naturally and actually even distracts us. So I see my Calculus 3 students sometimes try to kind of recall this formula in the middle of our new technique, and then it creates the mess. So if I said, you have to learn it, it's part of our curriculum, it will be on the exam, probably on one of the quizzes, and homework that I'll collect, but generally, when you finish this course and start Calc 3, just forget this formula. Anyway, where is this formula coming from? It's a fairly simple idea. So it's just when you do Riemann sum of the following formula. So that's formula from trigonometry, and that's the formula for the area of the angular sector. So if you have angle theta, and this is radius r, let's say, and this is radius r, what is the area of this circular sector? So you say the following. This is just a fraction of the whole circle. And the ratio is theta, relates to 2 pi, the same way your area relates to pi r squared. Pi r squared is the whole area. This is your fraction of the pi. So relates the way your angle relates to 2 pi as a full angle. When you solve for area, you get pi r squared over 2 pi times theta equals to area. You cancel pi and pi, and here is your area equals 1/2 r squared theta. And that's exactly what you have here, but why integral? Because then you cut this into, because this guy changes, so it's cut it into little slices. In each slice you can say, oh, it's almost circular, and then this is the angle d theta. For each of them, you apply the formula, take a Riemann sum, and this integral shows up. So it's obvious generalization of the old formula. As I said, it's fairly simple, but we'll have actually much better formula, easier to memorize in Calc 3. So until that time, we have to memorize this. So let's see one of the problems to see how it all works. So let's do that problem that we analyzed on the calculator. So it says find the area of one petal of, so number 8, area of one petal of, let's move this, of r equals 6 sine 2 theta. So what happens with that petal? Let's do the drawing. Maybe you remember it from calculator, but it could be done fairly easily with just a little table. You say, all right, here's my theta, here's my r, theta 0. Let me go around quicker. 0 pi half. So at 0, it's 0. At pi over 4, when you double it, you get pi half, so you get 6 maximal. And then it starts decreasing again because sine decreases and goes back to 0. So generally what happens, here you are at 6, and then you gradually grow. Here maximum, then you come back. So here's your petal. So what do you do then? Then using this formula, say area equals 1/2 integral between 0 and pi over 2 of r of theta squared, so I'll take whatever's on the right side, squared beta. You can see that in the notes, I actually didn't do this integral. I said the following, oh, but my petal is symmetric. So I can just calculate using symmetry half of it. And then so just calculate this part and then double it, because it's obvious that there is a symmetry, however you want to do it. Probably it's nicer that way. So here's what I'll do. I just change it like in the notes. It's really nicer. 0 to pi over 4, so just to calculate this part. But then I need to double it, and that will cancel this formula. Looks even nicer. And then how to solve this integral? Shouldn't be a problem. When I square this, I'll get 36. I'll pull it out. 36. Integral from 0 to pi over 4. And here is sine squared of theta. And then what do? I use our formula. Integral 0 to pi over 4. Sine squared is 1 minus cosine of the double. Since it's already 2 theta, it will be 1 minus cosine 4 theta over 2 theta. 36 over 2 is 18, so I can pull it out as 18. Integral of, so half is out. Integral of 1 d theta is just theta. Minus integral of cosine 4 theta is sine 4 theta over 4. Using our linear correction business. 0. So what would that give us? 18 times. When I plug in 0 in both of these expressions, I get 0, so nothing to worry about. And then I plug in pi over 4, I get pi over 4 here. And I get 0 here, because 4 theta is pi, sine of pi is 0. So I get 9 pi over 2. And that's how we use that area. When you're estimating, does it make sense that it's that big? So for example, if it was half of the circle of radius 3 would have 9 pi. So half of the circle, because what is here, if you put it here, it gets like half of the circle. And that's how it looks. So our next problem is problem number 16. Find the area between the loops of r equals 2 times 1 plus 2 sine theta. Of course, we can use calculator for this, but we can also draw it by hand if you just carefully analyze how the r changes with theta. First observation is that obviously, since we only have sine, that the graph will have this left-right symmetry, and so we don't have to analyze it all the way from 0 to 2 pi, which is, we can just analyze it between negative pi over 2 and pi over 2, which is the first and fourth quadrant. So here's what will happen. So if you plug in a few values, theta r, when theta is 0, we are here at 1, 2. And then r gets bigger and bigger, so at pi over 2, we'll get to 1 plus 2, 3 times 2, 6. So it gets bigger and bigger, and we know also that it will look like this. So that's all fairly simple. But some interesting things happen if we continue. So at pi, we will also be here back to 2. So angle is pi, that's angle is pi here, and then position is just r equals 2. But then, after pi, sine becomes negative, and very soon r will be 0. So when will that happen? 1 plus 2 sine theta is 0. Gives you sine theta to be negative 1/2, which is when theta is 7 pi over 6 first time. So here at 7 pi over 6, actually what will happen, our graph will get back to 0, like this. And then, so 7 pi over 6 equals 0. Then let's say at 4 pi over 3, the value will be 2 times 1 plus 2 times negative root 3 over 2. So that would be 2 times approximately, this is minus 0.7, so that's approximately minus 1.4. What happens now, actually when R is negative, we never discussed that before, we actually, so here's where 4 pi over 3 is. When R is negative, instead of the drawing where the ray is, we draw across. And this is where we are almost negative. And then at 3 pi over 2, so this is minus 1.4 approximately, will be at negative 2, which is again, we don't draw at 3 pi over 2, we draw across, and the value is 2. So generally, that's what we call the inside loop of this so-called nivasal. And then on the left side, we have a symmetry, and then here we get symmetry from this part. So generally, motion, the way we do it, goes like this, here, here, and up here, and then you go here, here, and we come back up to pi. All right, let me erase this. So what is it that they ask us to do? They ask us to calculate this area here. So here is the inside loop, here is the outside loop. So they want this area. Let me show you. Hold this, that's between the loops. This as well. So, how do we calculate that? We want to use that formula that we just developed, and that is when we have a region like this, if this is alpha, this is beta, and here is R equals R of theta, then this region, polar region, has the area 1/2 integral R of theta squared d theta, we know and beta. So if you wanted to see that region, then here's the best way to do that. Because otherwise, if you look at area between two loops and subtract, that would be quite tricky. Here's the better way to do this problem. Think of this, so I'll make a region a little bigger. That's not what they want, they don't want this. But this looks like a polar region, and actually this is what I'll call area A1. So that area A1, I can calculate, as I said, using this formula as long as I know the limits. And there is one more thing actually, you know what? I will not call, I'll change my mind. My area A1 will not be the whole thing. It will be just this right part. Why? Because of the symmetry, I can just, for the whole thing, just calculate the right half and double it. And of course, later on, I will subtract this inner part. So if I calculate the whole thing that I shaded green, and I subtract red, I will exactly get the area between the curves. And of course, then I will double it, and I'll get the area that they asked me to do. So it is somewhat complicated. So let's say the following. So here's our plan. Area equals 2 times area 1 minus area 2. So that's our plan. Now let's calculate each of them individually. So generally what? So for the green area, what do I need? Because formula is very easy. For a green area, it will be 1/2 integral R of theta squared, whose R of theta is, so it's our function, so it will be 4 times 1 plus 2 sine theta squared d theta. That's very easy. The only thing that's somewhat tricky is to actually see what are our limits. So what would be our limits? Let's recall what happened on our graph. We came here,
then we came here to 3 pi over 2, and then we just used symmetry, so I forgot what really happened here. So I was here when the angle was 4 pi over 3. So angle 4 pi over 3 gave me this position. Angle 3 pi over 2 gave me this. So here theta is 4 pi over 3. And then we drew across. So this came from theta equals 3 pi over 2. Where did I get this one? Also from the negative angle. Let me erase that one, because I need it here. So this came from the negative angle, and that angle is 5 pi over 2. And then this exiting position came from the same as 7 pi over 6, from 11 pi over 6. So that's the position where I start. So generally to get green region, I'll go from 11 pi over 6 until pi over 2. Of course, there's no natural continuation. Maybe I can go 11 pi over 2 to 2 pi, and then from 0 to pi over 2. That's much better to just call this negative pi over 6, which because that's this position could be also described as angle negative pi over 6, and that's what we'll do. So we'll go from negative pi over 6 all the way to pi over 2. So here's our integral A1. It might be a good idea, I'm not sure. I think it's a good idea to have everything set up here. What about integral A2? It will be the same integral, so I have here 4 times 1 plus 2 sine theta squared d theta. But what are the limits here? Let's recall what happened there. We entered that region at 7 pi over 6. It was here. So at 7 pi over 6 we came to 0, 4 pi over 3, 3 pi over 2. So this one's much easier to set up. So between 7 pi over 6 and 3 pi over 2. That's it. Everything left is just calculation. So let's see how do we calculate this. So this integral here will be, first I'll cancel 4.5, of course, and I'll pull that 2 out, integral between negative pi over 6 and pi over 2. I'll square this, I'll get 4, put 1 plus for sine theta, so square root binomial, for sine squared theta. How much is that? 2 times. And now I'll rush this a little bit. I'll start integrating, well, maybe not, maybe not. Let me wait a little bit. Pi over 2, 1 goes here, 4 sine theta, now a little trick. So I know, so it depends which part of the story you know about. Here's a little box 23. We very often use when we have sine squared theta reduction formula to be 1 plus 1 minus. Sorry, 1 minus cosine 2 theta over 2. So it's 4 sine squared theta when I multiply 4 sine squared theta. Is just, when I'm out there, I get 2 minus 2 cosine 2. And that's what I'm going to put here. 2 minus 2 cosine 2 theta. And then I can integrate 2 is out, who's here. 1 and 2 is 3. When I integrate it, I get 3 theta. Plus 4 sine theta, when I integrate it, I get negative. So minus 4 cosine theta. So this is done, this is done, this is done. And then what would this be? This would be minus sine 2 theta. I have the derivative of sine 2 theta is 2 cosine, linear correction is cancelled with 2. So it all looks good between negative pi over 6 and pi over 2. And then just easy calculation. What would that give us? 2 2 times. And what is the spread between pi over 2 and negative pi over 6? Or, no, why not? Make it so complicated. So this is 3 pi over 2 plus, because I'm subtracting negative, plus pi over 2. Then, this expression comes a minus 4 cosine pi over 2, and then plus 4 cosine negative pi over 6. Why plus? Because there is a minus and minus subtraction. Maybe I'm rushing this a little. I hope it's okay. Minus sine of pi and plus sine of negative pi over 3. Why again? So there is a minus in front of it and there is subtraction, and I double, so I hope that that's okay. A couple of things here should be cancelled. Cosine pi over 2 is 0, sine over pi is 0, so it looks like we are fairly close to finishing this. So it's 2 times, this is what, 2 pi? Cosine of negative pi over 6 is the same as cosine of pi over 6, which is root 3 over 2, so I'll get plus 2 root 3. And this is negative because sine is our function, so minus root 3 over 2. So when I double all this, I get 4 pi. Plus 4 root 3 minus root 3 will be plus 3 root 3. So that's our A1 that we need here. Now we need A2. What's the good news? The good news is that basically I can copy all this all the way to here because I'm integrating the same function and then just use different limits. So that would be, let me copy this, here it is. Maybe I'll use the opportunity to double it. Meanwhile, I'll give it current. So it's 6 theta minus 8 cosine theta minus 2 sine 2 theta, but not between these limits, but between 7 pi over 6 and 3 pi over 2. So how much is that? Between 7 pi over 6 and 3 pi over 2, they're just pi over 3. When you multiply it by 6, you will get 2 pi. Minus 9. Now I'll work on this a little better with parentheses. 8 cosine 3 pi over 2 minus 8 cosine 7 pi over 6. And minus 2 times sine 3 pi minus sine 7 pi over 3. So I need parentheses that I have that. Here it is. So I plugged in both of them. I kept my 2 outside here. I did each piece in different style, but that should be okay. So what happens again, cosine 3 pi over 2 is 0, sine 3 pi is 0. So we get the following 2 pi minus 8 times. Cosine 7 pi over 6 is negative, so it would be minus 8 times negative 3 over 2. And it would be plus 2 times, because this minus and this minus, but sine 7 pi over 3 is just the same as sine of pi over 3 because of sine 7 pi over 3 is here. So it's just 2 times root 3 over 2. I made a little error here. This minus and this minus should be plus. Because it didn't help me. And then cosine has its own minus. So what would that give me? It would give me what? 2 pi minus 4 root 3 and plus root 3 would be minus 3. You can calculate it. Let me check my calculations. Good. And that's it. So now, you know what I'll do? Since it's all very crowded, I'll just erase everything except what I need. So here are the pieces that I need. Here is my A2. Here is my A1. And then what do? I'll do what? I'll do 2 times A1 minus A2. So it will be 4 pi plus 3 root 3. Now I subtract minus 2 pi plus 3 root 3. And that would give me 2 times 2 pi plus 6 root 3. So that expression here is this part. Now after doubling, you get 4 pi plus 12 root 3. That's final answer. So this is a little bit kind of more complicated and more, not complicated, setup was not trivial, drawing it needed some time, and then also carefully doing the limit. But basically you will see in your calculus 3, we'll do something very, very similar. So I think here we are developing a very important skill for our calculus 3. All right, second part, arc length in polar coordinate. We basically use this. Let me emphasize something. When you have an object, so what is the main difference between polar coordinates and parametric equation? So when you have an object here, then when you do polar coordinates, we usually use polar coordinates to express the whole region. So whole region, then we have r and theta in that region. So region. For parametric equations, we just represent a curve. So curve where both x is function of t and y is function of t. So even if similar formulas appear, they are completely different things. But where do they match? And that's what we need actually here for the arc length. They match, and we already saw that in the previous section. For example, if I want to calculate, so here is the polar region, and I want to calculate the arc length. So I don't want area, I don't want whole region, I just want this arc length. So I'm moving on the curve, and then I'll say the following. All right, on this curve, my x and y coordinates depend on r and theta. But if r is the function of theta, then x equals r cosine theta is actually r of theta times cosine theta, and y is r theta sine theta. So generally I have parametric equation whose my parameter theta is parameter. And then what can we do? We will just call the arc length formula for parametrics, and we'll adjust it here. Basically formula, so theorem, or just formula. All the conditions for formula says the arc length L equals, for this region, you remember here is alpha, here is beta, so we have that L equals integral between alpha and this is r equals r of theta, square root r of theta squared plus r prime theta squared d theta. Here's the formula to remember. So how do we derive this formula? So why is this formula true? It's fairly simple. Why? Because we know that L equals integral between alpha and beta square root of x prime of theta squared plus y prime of theta squared d theta. What is this? This is just we are using this parametric equation. Parametric equation formula. And then what? From here we can just calculate easily to get this ready-made formula. We can calculate that x prime equals what? We use the product rule. So I'll just write it a little bit shorter. I'll just r prime, not r prime of theta. So it's r prime cosine theta plus r sine theta. What about y prime? Y prime is a what? R prime sine theta plus r cosine theta. And then what do I do here? I've squared and then add them up, so here's what happens. X prime squared plus y prime squared equals, when you square the first one, you get the following. R prime squared cosine squared theta minus 2r prime cosine theta sine theta plus r squared sine squared. Then the other one gives you r prime squared sine squared theta plus 2r prime cosine theta sine theta plus r squared cosine squared. So what happens if we add them up? These two guys cancel each other out because they are equal. And what about here? If I factor r prime squared, then I get cosine squared plus sine squared, which is 1 times 1. The same thing happens here, r squared times 1. So, if we calculate that and plug it in, we exactly get our formula. And that's alpha to beta squared root of r beta squared plus r prime theta squared. So that's our old formula, just adjusted for our new coordinate. So let's see one example how it all works. I'll just erase the derivation and write an example. Maybe even this. Maybe even this. Logical story. So we have a formula, we have the picture describing how that formula works, and let's do the problem. So a problem is problem number 38. And we are asked to calculate the arc length. The arc length of the curve. Arc equals a times 1 plus cosine theta. 0 less than or equal to theta less than or equal to pi. All right, so what happens? The generic picture, we will just draw the real picture here. Maybe a little table. So theta r. First, we see that it's cosine only, so the symmetry will be this symmetry, up down, because that's where cosine, because cosine is an even function. So generally, what are we going to do? Well, let's go when theta is 0, we will get a maximum value, which is 16. And then, so here is 16. And then it starts decreasing, and then at pi over 2, this becomes 0, so we just get 8. And then cosine becomes negative, so here is halfway through. And it gets even shorter, so at pi we'll get 0. So generally shorter on these rays, so generally it will come here. And obviously because of the symmetry, so we recognize our cardioid, and so here is the story. So what do we do here? So we want to describe this arc length. So what we'll do, obviously, because of the symmetry, we will just go here from 0 to pi. So we will just calculate this part in that way. So arc length equals r of theta is differentiable, so there are no problems here that we cannot apply our theorem. So what are the limits? Obviously, we start from theta to be 0 all the way to theta equals pi. We double it so that we don't forget that. And that's it. So generally, it's a good idea always to basically prepare your calculation, because I need r prime. Yeah, so r prime is a times a negative sine theta. And then what? R is a times 1 plus cosine theta. So r squared is 64 times 1 plus 2 cosine theta plus cosine squared theta. R prime squared is 64 sine squared theta. So when I add them up, you see I'm not calling the formula yet. I want to prepare it for it, so I get 64, 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta. And then you recall that this is 1, so I get 64 times 2 plus 2 cosine theta. Now we envision the following problem. That this is something that's not convenient for square rooting, and I need to square root it, so we might run into some algebraic troubles. But here is the way to handle them. Let's recall our reduction formula. Our reduction formula says that cosine squared theta equals 1 plus cosine 2 theta over 2. And we advertised that one a lot because they said, yes, we don't like to integrate square, we would rather integrate this, here's the price to pay. But now we'll actually go in the other direction. That's how math formulas very often work. One, sometimes we like it in one form, sometimes in the other. So what do we want? We actually want to trade form 1 plus cosine into the square so that I can square root it. It's not maybe too nicely convenient because I don't have cosine 2 theta, I have cosine theta, but that's easy, put theta half. So if I put theta half here, then twice theta half will be cosine theta. Looks much better. And now I'll multiply by 4, so I get 4 cosine squared theta half is 2 plus 2 cosine theta when I multiply by 4. And that's exactly what I have. So basically what I have is 64 times 4 cosine squared theta half. Okay. Let me get my calculation, looks good. So, I have a plus there, I'm just checking something. Yeah, it looks good. So, then I'll just go to the formula and put this expression under the square root, 64 times 4 cosine squared theta half, and here is the theta. And then what happens here, this is 2 times integral between 0 and pi. Integral of 64 is 8, integral of 4 is 2, that's why we want to multiply them. Integral of cosine squared theta half is cosine theta half, absolute value here. But now what? And now you see why it was good that we just reduced ourselves from 0 to pi and double it. Why? Because now if we go between 0 and pi, theta half goes between 0 and pi over 2, cosine is positive, so we don't need to worry about absolute value sign. So let's see what we have here. 8 times 2 is 16, times 2 is 32. Integral between 0 and pi, cosine theta half. And then what would they be? This is linear correction. Integral of cosine theta half is sine theta half with a minus. And between the limits, and then what? Times 2 for linear correction. So this would give me 64 times I flip the limits. No, integral cosine theta is plus sine theta. Sorry, I realized something's wrong here. Integral of sine theta over 2, 64 sine theta 2. And what would that be? Sine pi over 2. 0, sine pi that's our final answer, that this area equals 64. Does this make sense? I would say yes. So here's, how we make it. So this is 16, so this is a little longer you go around, so that's maybe 32 times 264. So our result makes sense. Let me double check in my notes. So the result is 64 and it is correct.